In this video, we will discuss how the agent trains using episodes and troubleshooting with reinforcement machine learning. In the last video, we covered the physics process function and how it updates the agent. Most of this function can be broken into 6 steps. First, the execute action function is called to move the agent based on the current action. Next, the reward and state values are collected using the getState and getReward functions. After that, the experience is stored in the replay buffer with the storeExperience function. Then the function checks for the end of the episode and resets if appropriate. The function also checks to see if it is time to train the agent or update the target network. Finally, the next action is chosen based on the collected state. This video will focus on steps 4 and 5, since the other steps were covered in previous videos. Episodes are used to train the agent. This means that the training environment is reset periodically. In this game, the agent is reset when it takes too long to collect a coin, or when it successfully collects all of the coins. Episodes make sure that the agent trains on the same task multiple times to learn the proper policy. In this game example, episodes might help the agent learn how to collect closer coins first, which will teach the agent that moving closer to coins is good. Later on, when the agent has trained and is exploiting its policy, this learning from early episodes helps the agent reach coins that are far away or difficult to collect. If the environment didn't reset each episode, the agent would only be able to collect close coins once and wouldn't be able to learn as much from collecting these coins. Since the environment is reset each episode, there are no long-term effects from failing. This means that if the agent collects one coin, but not all of the coins, it still has a chance to collect all coins in future episodes. If the agent gets stuck or falls off the map, it isn't punished for this after the episode resets. Episodes also help to keep track of an agent's progress. Since everything is reset each episode, the episodes can be compared to each other in terms of how long the agent took, how many coins it collected, or the reward earned during the episode. This information can be used to show the agent's improvement over time. In our example, the end of an episode is handled by resetting the agent, resetting collectibles, decaying the epsilon value to increase the agent's likelihood of using its policy to choose actions, and printing episode information to a file to analyze progress over time. The reset agent function sets the agent's position to its initial position when the last episode was started. Then its movement is reduced to 0, so that the last move it took in the previous episode doesn't impact the start of the new episode. Current jumps is reset to 0, so the agent can double jump from its starting point. Time since last coin collected is used to determine whether the episode should be ended. If the agent takes too long to collect a coin, the episode is reset, so time since last coin collected should start at 0. The previous state and action are set to null, since the last episode should have no impact on the new episode. The reset collectibles function on the right starts by subtracting the current score from itself to change the score to 0. Next, the function loops through all collectibles and resets them. Then the collected count is set to 0 to show that the agent hasn't collected a coin yet in this new episode. Now we will go through the train DQN function. This is where the Q network is updated using the target network and training experiences collected in the replay buffer. This function is called in physics process once every 5 moves. Train DQN starts by taking a sample from the replay buffer using the sample batch function covered in the last video. Then 2 arrays are set up to store batch states and batch targets. For each experience in our sample of the replay buffer, we separate it into the state, action, reward, next state, and done values. After this, the current values from the Q network are collected for both the state and the next state. In the image on the right, this function continues by determining the best next action from the next state. Since the Q values for the next state are in next Q online, we loop through these values to find the largest and its index. This index corresponds to one action, either jump, move left, or move right. This means that finding the highest Q value for the next state and saving its index gives us the best action that can be taken from the next state. After the loop, the next state is put into the target network to generate target Q values. And the target Q values for the next best action is determined and stored as double Q value. Now a variable named target Q value is set equal to reward. Target Q value is named this way because it is what the corresponding Q value in the Q network should move closer to. This value is not connected to the target network, even though it has a similar name. Once target Q value is set equal to the reward that was observed in training, the double Q value is added after being multiplied by a gamma discount value. This double Q value multiplied by gamma is used to predict the future benefit of taking the action that was chosen during this experience. The target network is used to estimate this future value since it is updated less frequently than the Q network. In the physics process function, the target network is set to the Q network values every 1,000 moves. The target network helps to keep updates stable for the Q network, which is used to select moves. Once the target Q value has been calculated, the Q values from the Q network are copied to target Q values. And the Q value in this list for the target action is changed to reflect the target Q value that was calculated. The state and target Q values are added to the batch states and batch targets arrays. Once the state and target Q values for each experience in the batch have been added to the arrays, the Q network is updated based on these values. Some common problems for a reinforcement machine learning agent are overfitting and underfitting. Overfitting happens when the agent gets stuck with a policy that is non-optimal and hard to change. With an overfit policy, the agent would likely move in a similar way each episode without collecting all of the coins. During this project, we ran into an issue where the agent learned to jump close to its starting location without moving to collect coins. It is possible that this issue was caused by overfitting, since the agent moved in the same way during each episode. To fix overfitting, it might help to decrease the number of nodes in the queue and target networks. This will keep the agent's policy simpler and help it to generalize to new environments. Adding some randomness to the environment during training may also help the agent learn a more general policy. Lowering the learning rate could help to fix overfitting, since it will take the agent more episodes to form a rigid policy. Underfitting happens when the agent does not have a clear policy. The agent may seem to make random moves even when the epsilon value is low. Underfitting can be fixed by increasing the number of nodes in the neural networks. This allows the agent to learn a more complex policy that fits the environment with more detail. Decaying epsilon more slowly may also help, since the agent will be encouraged to explore its environment more while training. Increasing the learning rate may help the agent avoid underfitting by giving each move a larger impact on the policy. If the agent is underfitting on its environment, it is also possible that more training is needed to create the policy. The queue network and target network are neural networks for the agent. If you modify one of these networks, the other should be changed to match. Also, when changing the number of nodes, you should increase or decrease the middle two values and not the outer two. The outer two values, 13 and 3, shouldn't be changed unless you add another input or output value. The epsilon value in hyperparameters is the beginning chance that the agent chooses a random move instead of one that is based on policy. Since this value represents a percentage, it should be between 0 and 1. This value does not impact the rate that epsilon decays, since epsilon decay is done in the physics process function at the end of each episode. Gamma determines the impact of future moves on Q value updates. Max buffer size changes the number of experiences that are held in the buffer. Increasing this value allows the agent to update based on the results of older experiences, while decreasing this value forces the agent to choose from newer experiences. Batch size is the number of experiences chosen to update the agent each time the train DQN function is called. Step count and train counter should be left at 0, since these values count the number of steps taken by the agent to determine when an update should occur. Train frequency impacts how often the queue network is updated. Currently, this is every 5 moves, but could be set to update more or less often. This is a video of the agent training. This video was made when the agent just started training, so most of its moves are random. This agent will need at least a few hundred episodes to train a proper policy, but may take a few thousand. And then you can see the reset there. This is the end of our video series on the basics of reinforcement machine learning. Thank you for watching.